So, remember long ago we did this 2-stage op amp. And finally, all these current sources are will be realized using MOS transistors, right. So, we do not, I mean, this for the time being we just assume that they are ideal current sources, and here we said that we are going to have some kind of voltage control voltage source that can be either a NMOS or a PMOS common drain amplifier. So, this is VDD. So, which is the positive terminal of the op amp and which is the negative terminal of the op amp? Let us call this A, let us call this B, A is negative, B is positive, and so if you yank B up, this is going to go down, if this goes down, this goes up, if this goes up, that goes up, right. Okay. So, and remember, and let us assume that the output resistance of a NMOS transistor is so let us call that the GM of each of these NMOS transistors is GM1, and RON, and this is basically ROP is the output resistance of each of these PMOS transistors. Okay, and this is GM2, or I am going to call this R2 just for because it is the second stage. All right. So, now assuming that everything, I mean, remember that you can never operate an op amp in open loop, it is part of some negative feedback loop, and therefore, the potentials at A and B will be the same, and consequently all transistors are operating in saturation, everybody is happy. So, now the question is what is the what do you call the small signal equivalent as far as the what do you call this thing is concerned, small signal operation is concerned. But remember that we said that every transistor, every node is associated with some parasitic. So, this is I am going to call this C1, right, and that includes what all parasitics does C1 include? The drain parasitic of the input NMOS transistor, the drain parasitic of that PMOS transistor, and the gate parasitic of the second stage. Okay, all of them are in parallel, so we can basically club every one of them together, and so that is C1. Similarly, C2 is the input capacitance of the next stage and all that stuff. So, that is basically C2. Okay, and so and there is going to be some small capacitor here, which I will call C mu. Okay. Now, what is the model for the first stage? Remember, what did we say was the DC gain? So, this is, let us call this minus Vi by 2, this is Vi by 2. Okay. So, the differential input is Vi. So, what is the effective current going in here? What is the effective current going in there? That is nothing but is GM 1 times Vi, okay, and what is the output resistance of the first stage? RON parallel, ROP, which I will call RON parallel ROP, I will call R1, that is basically R1. This is C1, and this is GM2, RO2, C2, and then there is some, this is V. I have just kept that that output buffer as a as an ideal VCVS, simply because remember that the bandwidth of that common drain amplifier actually very high, and we do not have to really complicate our lives simply because of that. There will be some bandwidth but that will be so high that we do not have to worry about. So, this is the model of the whole two-stage op amp. I think we have forgotten the scene. Okay. So, does this look familiar? Have we done this before? Have we done this before? Where have we done it? Yeah, because this is basically the picture is exactly the same as the common source amplifier. Remember, in a common source amplifier we had a voltage source, a source resistance, then CGS, right. So, this is recall common source. So, this is Vi, this is Rs, this was CGS, CGD, this was GM Vx, and this was RL, I think, and CDB. Right. What is the only difference between, apart from changing what we call each one of them, this is GM2 times Vx. Apart from minor changes, right, the only other change is that here we had a voltage source in series with a resistance. Here you have current source in parallel. So, what can we do? Yeah, well, if you want to just use the same formula, this is simply R1 and GM Vi GM1 R1 Vi. Okay. So, what was the, can we just simply look at the at this and write down the formula? What is the DC gain? So, this is minus actually, I think, right? What is that? So, it is, or it is plus? It is plus. Okay. So, what is it? this is minus, so minus into minus will give you plus. Yeah. Okay. So what is the DC gain? Not this one. This one we've already done. I am asking you for the one upper one. What is the point in redoing the one which you've already done before? I mean, this is R2. Okay. Minus GM2 times GM1 R1, GM2 R2 is the DC gain, right? Then do we expect to see a right half plane 0? GM2. So, this is going to be 1 minus SC2 over GM2, okay. This divided by 1 plus S times R1 times C1 plus C mu into 1 plus GM2 R2 plus R2 times C2 plus C mu plus S square times R2 R1 R2 times C1 C2 plus C2 C mu plus C mu C1. C mu, not C2, sorry, C mu. Yeah. Okay, I mean, this is just the same expression that we have done earlier, except that we replace RS with R1, CGS with C1, CGD with C mu, and CDB with R, with C2, RL with R2. Okay. So, the DC gain of the op amp as expected is GM1 times R1 times GM2 times R2. There is a right half plane 0. There are 2 poles, correct. So, now the question I'm going to ask you is, what, I mean, it's a second order system and there are 2 poles. What comment can we make about the locations of the 2 poles? In other words, are the 2 pole locations like comparable, or are they like see R1 C1, R2 C2 etc. will all be comparable, right? Because C1 C2 are parasitics of the transistors, R1 R2 the output resistances. They will not be the same, but they'll be comparable. So, with that, what comment can we make about the relative locations of these 2 poles, of the 2 poles of the system? Why? But C mu is also a small number. Yeah, so C1, yeah, that's what see, basically all that this is saying is that this and this are comparable to each other. In other words, I mean, in other words, see, if that C mu was not there, what comment can we make? You have a first stage which has got a pole at R1 C1, second system has got a pole at R2 C2, because C mu there is some small interaction, but the 2 poles are comparable. There is no, I mean, it's not as if one is much faster than the other, or one is much slower than the other. They can be expected to be roughly near each other, right? Okay. So, in other words, this for all practical purposes, therefore, the 2 poles are comparable, right. So, the 2 poles are comparable. I mean, we can use our earlier analysis where 2 poles are comparable basically means that they're somewhat close to each other. So, so what happens if you enclose this op amp in a negative feedback loop is to get an idea of what happens. you can imagine that the two poles are the same. What will happen when you close the loop? If the two poles are exactly the same, pardon? We have done this before, right? You have a two pole system where both the poles are at the same location. What comment can we make about the closed loop system? Yeah, but what is the problem? How? So, the quality factor, the closed, so if we just use the op amp as is, the closed loop system, might technically be stable, right? But in reality, the quality factor of the closed loop poles is the square root of a naught square f, right, which is a naught root f, and a naught in this case is gm1 r1 times gm2 r2. So, square root is basically of the order of gmro times whatever feedback factor there is, right, and therefore, what do you call the closed loop system is will have a Q which is of the order of GMR by 2. If GMR is 100, some maybe 40 or 50, GMR by 2 will basically be something like 20. A closed loop system will have a Q of 20. That basically means it will ring 20 times before it dies down. Does it make sense? So, so for all practical purposes, therefore, this op amp is unusable as it stands. So, what do we do to make it usable? What is the principle? We introduce a dominant pole, right, okay, so that these two poles can be widely separate. Does it make sense? Okay. In other words, the dominant pole is much lower than the other pole. So, and as you know, to slow something down is very easy, right. What do you think we can do? We can take a big fat capacitor, and there are and we can place it in parallel with any one of the capacitors that are already there. For instance, we could place a big fat capacitor in parallel with let me call that CC, in parallel with C1 or parallel with C2 or in parallel with either C1 or C mu or C2. Okay, so 3 possible choices, right? Okay. Then somebody brightly came up with the idea, I will do both C1 and C2. What is your opinion? Pardon? Yeah, both will both will shift low, that is no good, right. So, you only want to put it across either one of these. So, you have 3 choices, correct? Okay. So, which do you think is the smartest thing to do? Well, by symmetry, whether you do it to C1 or C2, it looks like it doesn't matter much, right. Why do you say C mu? So, basically, as you can see, if for a fixed amount of capacitance, right. So, if you add capacitance just in parallel with C1, C1 will become C1 plus Cx. So, this term will become what do you call the time constant will increase by R1 times Cx that you add, whereas if you add it in parallel with C mu, you can see that capacitance is getting multiplied by the effect of C mu is getting electronically multiplied due to the Miller effect, right. Okay. It is very easy to understand what this Miller effect is. Okay. So, let us say you have Usain Bolt, who's running at Bolt or whatever he is, right, runs buku fast, right. So how do you how can you slow him down? Well, you can say, oh well, it's very easy, right. You take a bag of sand and you tie it up to one of his foot, right, or you can tie it to his foot or you can tie it to his hands, okay, and then automatically it will slow down. That's what capacitance does, okay. But I don't know if you have watched the news, but sand is very expensive, right, and sand is silicon, so just like silicon area, it's very expensive, right. So you want to be able to slow him down to the same extent by using the least amount of sand, correct. So so what do? You watch the video in slow motion and then you recognize that every time Usain Bolt runs, what does he do? His hand is running this way and his leg is kicking that way. Both of them are in the opposite direction. So you get the smart idea that I will try a thin string between his arm and his leg. So he is basically himself slowing him down. I don't have to really put too much sand. That's basically what's happening with the Miller effect, right. Why is this? What is this big deal? What is the electronic multiplication of capacitance? How is a small capacitor made to look big? Why? Because when the gate is going this way, the drain is going the opposite way. So if you put an elastic between the two, then both of them are trying to pull towards each other, right, therefore slowing the whole system down, right. So the basic principle behind the Miller effect is that if this goes up, this is going down by a large factor, and therefore even though you are putting only a small capacitance, right, the amount of current that's flowing through C mu is multiplied by this 1 plus GM2 R2 factor, right. So the smartest thing to do is basically say, well, neither C1 nor C2 get anything. We just simply replace. I mean, you take a big fat capacitor and put it between the gate and the drain of the second stage. So that's basically this is the C sub C, right. So Cc is the Miller compensating capacitor, which introduces the dominant pole, right. So this becomes Cc, this becomes Cc, this becomes Cc, all right. And by introducing Cc, what have we done? We have shifted the poles apart, right, so that the two poles are separated from each other. So now, so if the two poles are separated, they must be of the form, so 1 plus S by omega d times some 1 plus S by some omega naught, where omega d is much smaller than omega naught, correct. So this is approximately therefore equal to 1 plus S over omega d plus, what are the two S terms? S by omega d plus S by omega naught, okay, and S square by omega d omega naught, okay. So that basically, that S by omega naught term can be neglected, and basically you have S square by omega d omega naught, okay, all right. And so what is omega d? What is omega d? Yeah, it's basically, it's 1 over all this entire term. So, which of these terms can be neglected? Well, in the second term, we can neglect C2, right, and in the first term you can neglect C1, you can neglect 1, and uh, uh, so basically you have R1 CC GM2 R2, and you have R2 CC, but if the R1 and R2 are comparable, what can you neglect? I mean GM2 R2 R1 CC and then R2 CC, which can you neglect? Yeah, this is basically, so this term is approximately equal to S times R1 CC GM2 R2. So, what is the dominant pole? One by R1 CC times GM2 R2. Does it make sense? Okay. I mean, why does, I mean, of course, this comes out of the math, but is there an intuitive way of simply looking at it and telling, figuring out why it makes sense? What is the capacitance looking in here? C1 in parallel with? Very good. C1 plus CC multiplied by 1 plus GM2 R2. So, if GM2 R2 is very large, 1 plus GM2 R2 is the same as GM2 R2. So, the looking in capacitance is approximately equal to C1 plus CC times GM2 R2, which is approximately equal to CC times GM2 R2, and the resistance is R1. So, the pole at that first node is going to be 1 by R1 times CC GM2 R2. So, that makes sense. That dominant pole being 1 over R1 R2 CC GM2, that makes sense. I mean, the second pole of course is far away, so we don't, I mean, so it so as far as the dominant pole is concerned, this is all that we need to worry about. So, what is the second pole therefore? What is omega naught? Yeah. So, basically we know this the product of the two poles. So, what should we do? It's this is nothing but omega d times omega naught. So, omega naught therefore is nothing but, this is nothing but 1 by omega d omega naught. So, what is omega naught? It is 1 by R1 R2 times C1 C2 plus C2 CC plus C2 CC C1. This times R1 CC GM2 R2. Okay. So, fortunately these two guys go away. Okay. Are we? Yeah, this is fine. So, this is let me write it in a slightly different way. This is GM2 over C1 plus C2 plus C1 C2 over CC. Okay. All right. So, why does this make sense? Okay, let's take a look. So, basically at frequencies much beyond the dominant pole, right? Will which of these impedances dominate? Which one will be higher, the resistance or the capacitance? The capacitance. So, at very high frequencies, therefore, one need not worry about current through the resistors at all, whether it is this resistor or that resistor, right. So, the question is, what is the pole frequency because of the rest of the circuit? Okay. So, what is the resistance looking in here? What is the impedance looking in there? What is Vx? If I apply a test voltage here, what is Vx? Yeah, that's nothing but Vx is nothing but V test into Cc over C1 plus Cc. So, what is the current flowing here? This times Gm2, correct. So, what is the resistance looking in? It is nothing but C1 plus Cc over Cc times 1 over Gm2. That is the resistance looking in there, and apart from this, there is also a current flowing through that guy. What is that current? It is just Cc and C1 in series. So, what is the effective capacitance looking in there? C1 Cc by C1 plus Cc. So, what is the time constant associated with that node now? It is the resistance times C1 Cc by C1 plus Cc plus C2. Correct. So, what is the pole frequency therefore? Omega naught therefore must be 1 over Rc, which is Gm2 C1 plus Cc by Cc times C1 Cc plus C1 C2 plus C2 Cc by C1 plus Cc, correct. So, that basically this Cc comes here, right. So, it is Gm2 Cc by C1 Cc, C1 C2, C2 Cc, and that is basically that is that is basically what the expression you get after running through the algebra. This is what you get, right. But the intuition behind why you get this result is that at high frequency, the current flowing through R1 and R2 are all negligible, right, and the system you have is basically just C1, Cc, Gm2 and C2, and the time constant corresponding to the pole frequency corresponding to that system is this expression over here. Okay. All right. So, we will so I will stop here, we will continue in the next class.